to this class. I am Ubani Kirsten, and I'll be taking you on the subject chemistry. The theme of our lesson today is the chemical world, and we'll be looking at the topic gas laws, part 1. By the end of this lesson, you should be able to explain the Kelvin scale of temperature and its relationship to Celsius scale. You should also be able to explain the effect of pressure on the volume of a gas. We'll see that when we'll be looking at gas laws. And lastly, you should be able to show how heat affects the volume of a given mass of gas. We'll be looking at Charles' law. Now, it is not only solids and liquids that can occupy a space or be confined in a vessel. Gases as well can be confined in a space and they can occupy a space. Okay, for example, the balloon. When you get an empty balloon and you fill it with air by blowing air into it, you see that when you tighten it, the balloon remains the way it is because the air has occupied the space in that balloon. So that goes to tell us that gases occupy space as well. Of course, air is a gas. Okay. Now, there is a particular way that gases behave when they are confined in a system or they are placed in a closed system. A closed system simply means a system that has a seal on it, okay, in which no other force such as environmental or atmospheric forces act on. Okay, an open system is one that is open. The balloon we talked about, okay, when you tighten the knot, that balloon becomes a closed system because nothing can go into that balloon again and nothing can come out of it. So an open system, you can see here, it's open. There is no lid closing it. So the atmospheric pressure and other materials can go into it, and also the substance in it, if it's a gas or if it's a liquid that vaporizes it, can actually go out into the atmosphere. But a closed system, as you can see here, the one that has something or a lid on it, can see that even when there is evaporation and condensation, it's going to happen within this system. So this is the difference between an open system and a closed system. And in this lesson, we are talking about how gases behave in a closed system, okay? Now, there are laws that govern or that tell us how gases behave. These laws are called gas laws. So, gas laws apply only to gases, okay? As the name implies, gas laws. And it deals with how gases behave with respect to pressure, volume, temperature, and number of moles or mass of the gases. So these are variables that this gas law tries to talk about, okay? When you change the pressure of a gas system, what happens to that system? When you change the temperature by either increasing or decreasing it, what happens to the gases inside that container? So that is what these laws try to talk about. Gases have the highest kinetic energy, okay, making their rate of movement and collision very high. In our previous lesson, when we talked about the states of matter, we talked about how solids have the least amount of kinetic energy, and because of that, they do not move. Actually, they just vibrate about in their container, okay? The molecules of a solid just vibrate, and that is what gives them the shape that they have because they do not move about. In liquids, the kinetic energy is quite high, but not as high as the kinetic energy that gas molecules possess. And that is why liquid molecules can flow or glide over themselves. But for gaseous molecules, we are saying that the kinetic energy is so high that intermolecular forces are even negligible. So these gas molecules can move at very fast rates and collide with themselves and with the walls of their container at a very high rate. Now, substances in the gaseous state have characteristics that are different from substances in the solid, liquid, or even plasma state of matter. So, many early scientists such as Boyle, Charles, and Dalton studied the physical behavior of gases, okay? Gay-Lussac, which is another scientist, studied the chemical behavior of gases. Now, the laws they proposed about what they observed were named after them. And some of those laws are Boyle's Law, named after the scientist that proposed this law, Robert Boyle. Then we have Charles' law, named after Jacques Charles. We have Gay-Lussac's law, named after Joseph Louis Gay-Lussac. We have Avogadro's law, named after Amedeo Avogadro. Then we have Graham's law, named after Thomas Graham. Well, for this lesson, we'll be looking at the first two laws, okay? Then the rest we'll look at them in our next lesson. Now, gas laws can be explained by the kinetic theory of matter, okay? This kinetic theory tries to make a lot of assumptions, okay, about how an ideal or perfect gas behaves or should behave, okay? But in reality, actually, gases do not follow these assumptions 100%, all right? But for the sake of what we study in the science world or for chemistry, it is good that we go with the assumptions given for a perfect gas. All right, so these assumptions were made for perfect gases, gases that are supposed to behave in a particular way under any condition. So some of these assumptions are: one, that gases consist of molecules that move randomly in straight lines. Okay, the movement of gas molecules are straight. Okay, it is not curved. All right, so we can see here, say, a gas molecule moving from point A to B. I can see that all movement it makes and the collision it makes are straight. It goes from point A down to another point, and from this point it makes another straight movement, and it keeps making very straight movements until it gets to point B. So the assumption is that gas molecules move in a straight line. They collide with themselves. Of course, two gas molecules can collide within a closed system. They can collide with themselves. They can also collide with the walls of their container. Another assumption is that the collision of gas molecules on the walls of their container brings about gas pressure. All right? So you can imagine that when millions or several gas molecules are colliding on the walls of their container, it exerts a certain amount of pressure on that container. And that pressure is what we call gas pressure. We're looking more at gas pressure in the course of this lesson. Another assumption is that the actual volume occupied by the gas molecules is negligible relative to the volume of their container. Imagine gas molecules are so tiny. They are extremely tiny that one collision on the wall of the container would really not make any difference, would not even be noticed. Okay, so it's saying that the actual volume that these gas molecules is going to occupy is negligible, all right, compared to the volume of their container. Another assumption is that lighter gas molecules will move faster than heavier gas molecules in a given vessel. Of course, that makes sense because, for example, let's use solid particles, okay? If you have maybe a piece of paper and a piece of glass on a table and you blow air on both of them at the same time, what happens? You realize that the piece of paper that, of course, is lighter or less dense is going to move or fly off that table, while the piece of glass will need you to apply more air pressure before it can move, right? So that also applies to gases. Lighter gas molecules, if they are placed in the same container with heavier gas molecules, the lighter ones have the tendency to move higher or faster than the heavier gas molecules. Now, the collision of gas molecules is perfectly elastic. This simply means that when there is collision between two gas molecules, energy is not lost, neither is energy gained. For example, if two gas molecules represented by 2 points, one is coming with an energy of, say, 40, and another is coming with an energy of 60. This totals an energy of 100, right? Now, when they collide, one of them may lose its energy and the other one may gain energy. So this one may gain energy and now move at a rate of 70, and this one may lose energy and move at 30. But when you still add this 70 and 30, we are still going to what? Have 100. So energy they had before collision, okay, and energy they had after collision is the same, although energy has been transferred from one gas molecule to the other. So that is what this statement means, that the collision of the gas molecules is perfectly elastic. Energy is not lost, neither is energy gained. Even when they collide with their container, okay, what happens is that they just rebound like an elastic ball, but energy is not lost or gained. Another assumption is that the forces of attraction or repulsion between gas molecules are negligible. An ideal gas does not really have intermolecular forces, okay? Solids have the highest intermolecular forces. Because of that, they are compacted, they are together. Liquids have a reasonable amount of intermolecular forces, but gases have the least amount of intermolecular forces, so much so that the force of attraction or repulsion between them is highly negligible, and that is why they can move at very fast rates and away from themselves. As you can see in this image, you see that one gas molecule can be here and another can be another considerable distance away from the other gas molecules, because there is no force of attraction binding or holding them together. Another assumption is that all gases have the same average kinetic energy at a given temperature. At a particular temperature, all gases have the same average kinetic energy. So these are just a few of the assumptions of this kinetic theory that we are going to be making reference to in the course of this lesson. There are a lot of other assumptions, and I'm sure if you go through your notebooks or you check online, you'll be able to read more on kinetic theory of gases. Now we'll be looking at some key notes making reference to these as we move in the lesson. So it's important that you get to know what they are. So we'll be looking at what gas pressure is, standard temperature and pressure, STP. I'll be looking at Kelvin scale versus Celsius scale. Gas pressure. Gas pressure, we've said, is the pressure that gas molecules exert on what? The walls of their container. And of course, we have noted that gases have the highest amount of kinetic energy. Now, when gaseous molecules are contained in a vessel or a container, they move randomly about at high speed. As we have noted, they move randomly about at high speed and in a straight line. Okay, so they are colliding with themselves, okay, and they are colliding with the walls of their container. Now they exert a very small force on the walls of their container because of how small they are. Remember, we said that gas molecules are so small. Of course, you can't even see them with the naked eyes because of how small they are. But given how numerous, okay, and evenly spread out they are, they tend to exert constant force or pressure on the walls of their container. So it's like saying, for example, just one gas molecule exerting its force on the wall of the container is really not going to make any difference. But imagine millions of these same gas molecules, several gas molecules exerting their force on the walls of the container. Definitely it's bound to have some form of pressure, okay, on the walls of that container. So that pressure that those millions of gas molecules exert on the walls of their container is what we call gas pressure. Okay, therefore, we can say that gas pressure is the force that gaseous particles exert per unit area of the wall. Now, the force gases exert is constant for every unit area of the walls of the vessel in which they are contained in. Okay, so if you have a vessel, okay, of course, it's going to contain several units. And we are saying that if this is a unit, that the force that the gas pressure is going to exert on this unit, okay, is going to be constant or fixed with the force that it exerts on another unit of the container, and with several units forming the vessel or container in which the gas is contained. We are saying that this pressure, okay, exerted is constant for every unit, for each given unit area of the walls of the vessel in which the gas is contained. Gas pressure, we measure it in atmospheres or millimeter mercury. The SI unit for measuring pressure is the Pascal, which is seen as the newtons per square meter with this symbol. Alright, so that's that on gas pressure. Now we'll be looking at standard temperature and pressure. The volume of a gas can be affected by a change in temperature and pressure. We are saying that if a particular gas has a certain volume, okay, that volume is going to be affected if, say, temperature of the system is changed. For example, if the temperature of the system is increased, that is, more heat is applied on that system, the volume of that gas is going to change. Okay? If temperature is reduced, the volume also will change. Pressure, likewise, if pressure is increased or reduced, it is going to affect the volume of that gas system. So, we know that different parts of the world have different temperatures. So, for example, let's say two scientists or two students, science students, we are working in two different regions of the world. Say one is in a temperate country such as Japan, okay, that is quite cool, maybe in a cool environment, okay, and another person is maybe in a tropical country, say Nigeria, that maybe is hot, all right. We are saying that if they are working maybe on a particular gas, maybe such as methane, all right, the volume of this gas is going to be affected by the difference in temperature of these two regions. So, because of these differences that may arise with scientific experiments when dealing with gases, scientists now came up with what is called standard temperature and pressure at which gas volumes should or can be calculated. All right, because of these differences that may arise due to the environment in which an experiment is being carried out, they said, okay, instead of having those differences, let's just have a standard at which we can measure these volumes so that we will not have confusion in measurements. So they came up with this standard measure for temperature and pressure at which gas volumes are given. So the standard temperature and pressure given were 0 degrees Celsius or 273 Kelvin as the standard temperature known as ST, okay, symbol ST. Then for pressure, they had 760 millimeter mercury or 1.01 times 10 raised to power 5 Newton per square meter as the standard pressure. Hence the phrase standard temperature and pressure. Okay, so because in the course of our lesson, we may be dealing with these standards. All right. Now, Kelvin scale versus Celsius scale. What is a Celsius scale? The Celsius scale is a scale used in the measurement of temperature that uses the boiling and freezing point of water as its mark. Okay, so it uses 100 degrees Celsius for the boiling point of water and 0 degrees Celsius for the freezing point of water. It is also called the centigrade temperature scale, and it has the symbol, the popular one we write as degree Celsius. Kelvin scale. The Kelvin scale is a scale of temperature designed so that 0 Kelvin, okay, 0 Kelvin is identified as absolute zero, all right? And the triple point of pure water is identified as exactly 273.16 Kelvin and 611.66 Pascal. So what is absolute zero? Absolute zero simply is the temperature at which the molecules of a substance has the least amount of energy. That is what we call absolute zero. And the Kelvin scale is designed so that the 0 Kelvin, all right, is going to what be identified as this what absolute zero. So at 0 Kelvin, we are saying that it should be the point or the temperature at which the molecules of a substance has the least amount of energy, and this is equal to what? Minus 273.15 degrees Celsius. So 0 Kelvin is equal to what? Minus 273.15 degrees Celsius. All right. Then the triple point is the temperature and pressure at which water exists in equilibrium in the solid, liquid, and gaseous states. All right? So the Kelvin scale is designed so that the 0 Kelvin is identified as absolute zero, and the triple point of pure water is identified as minus 273.15 Kelvin. Now, when the difference between the freezing and boiling points of water for both Celsius scale and Kelvin scale is measured, okay, a difference of 100 degrees is obtained. Okay, so we know that the boiling point of water is 100 degrees Celsius and its freezing point is 0 degrees Celsius. All right, and for the Kelvin scale, the boiling point is at 373 Kelvin, and the freezing point of water for Kelvin is 273 Kelvin. All right. Now, if you are to calculate the difference between these boiling and freezing points, we'll see that it is the same. 100 minus 0, of course, is 100, and 373 minus 273 is also going to give us 100. So that is where we say that the Kelvin scale has the same magnitude as the Celsius scale. But in the scientific world, the Kelvin scale is preferred to the Celsius scale. Therefore, it has been adopted as the international standard for the measurement of temperature. So, let's say you're given a calculation, okay, and you are told to convert a Celsius scale to a Kelvin scale, or to convert from Kelvin to Celsius scale. How do you do that? So it's simple. To convert degrees Celsius to Kelvin, we use this formula. So whatever that was given to us in degrees Celsius, we add 273.15 to it, and we'll get our answer in Kelvin. So for example, if you're given 25 degrees Celsius, okay, and you are told to convert it to Kelvin, all you need to do is to what? Add 273.15, and whatever you get becomes your answer in Kelvin. Now, also to convert Kelvin to degrees Celsius, we use this formula. Whatever is given to you in Kelvin, you subtract 273 from it, and whatever you get as your answer will be in what? Degree Celsius. So if you're also given, say, 400 Kelvin, okay, to convert to Celsius scale, all you need to do is to subtract 273.15 from it, and whatever you get will be your answer in degree Celsius. So this is how we go from Kelvin to Celsius, or from Celsius scale to Kelvin. So these were important things for us to note before we go into Boyle's and Charles' law. So Boyle's law states that the volume of a fixed mass of gas at constant temperature is inversely proportional to its pressure. So, as I say, this law is a pressure volume law. Okay, so it tries to say what happens to volume when pressure changes. Okay, and it looks at these two variables when temperature is kept constant. So the temperature of the system should not be changed, and also the mass of the system should not be changed. The two variables that change here are volume and pressure, and it's telling us that when the mass of a gas and the temperature of the system is kept constant or fixed, okay, that volume will be what? Inversely proportional to the pressure of the gas system. Inversely proportional or indirectly proportional. So this simply means that when one variable is going up or increasing, the other variable is decreasing. They are indirectly proportional to themselves, okay? Like they are moving in opposite directions. When one is going up, the other is coming down. Or when one is coming down, the other is going up. So that is what we mean by the volume of the gas being inversely proportional to the pressure of this gas. So in other words, if we were to force a given amount of gas into a smaller volume, okay, the pressure exerted by the gas particles will increase, provided that the temperature of the system stays the same or remains constant. So we can mathematically represent Boyle's law with this, where volume is inversely proportional to pressure, okay? So we can say V is equal to K over P. This K is a constant. Now, Boyle's law can be easily explained with a closed vessel or container with gas molecules in it, okay? So if the volume of the system is reduced, pressure is going to what? Increase by a similar proportion. So for example, if the volume is increased 10 times, the pressure will decrease 10 times. All right, so that's why we say they are inversely proportional. It is with the same proportion that the volume increases that what the pressure would decrease. So this relationship can further be represented with this equation where P1V1 is equal to P2V2. Remember that P1 will be talking about what? Pressure. All right. Now, the V1, okay, is going to be the volume at what? Pressure 1, while V2 represents volume at pressure 2. Now, let us look at a more inclusive definition of Boyle's law. We have said that two variables, temperature and number of moles, okay, or mass of the gas molecules will be constant, while the variables that change are the pressure and volume. So a more inclusive definition will be that within a closed system, because whatever we are talking about is happening in a closed system where no other kind of force such as atmospheric pressure is acting on the gases. So we can state that Boyle's law states that within a closed system, the pressure exerted by a given mass of gas or fixed mass of gas is inversely proportional to the volume it occupies, provided that the temperature and mass of gas remain constant. And this is a graph showing us the relationship between volume and pressure. We can see that when volume is low, pressure is high, and where volume is high, pressure is low. Let us see how kinetic theory explains Boyle's law with this experiment, okay? Now, we have said before that pressure is caused by gas molecules hitting the walls of their container, right? And we talked about gas pressure, all right? So we know that pressure is caused when gas molecules hit the walls of their container. Now, assume you have a fixed mass of gas at what? A constant temperature, let's say at room temperature. The mass of gas, okay, is in a closed system. The first image here, let's say you started out with this container. The temperature is constant. The mass of gas, of course, is constant. We are not adding or removing gas molecules, all right? Now, if you are to reduce the volume of this container by pushing down the piston, okay, this is what we call the piston, and it should be movable for this experiment, okay? It should be such that it can be pushed down or pulled up. Now, if this piston was to be pushed down, as we see in the second vessel, okay, we'll see that when we push down the piston, we are reducing the volume of the gas container, okay? So if we reduce this volume by pushing down the piston, pressure will increase within the gas molecules so that they will hit the walls of the container more often. It's just like having maybe in a particular room of this size, okay? So say this is our closed system, and perhaps you have 5 individuals. You see that they are well spaced, okay? The pressure they will exert on themselves will be very, very slow because, or very, very reduced because they are not together, all right? Now imagine that these same 5 people we are put in a smaller room, maybe of this size. We can see that the spaces between them, the distance between them has been reduced. So there is every possibility that the pressure will increase. They could collide more with themselves, okay? And they can generate higher pressure when they are in a smaller room. Same number of persons, but difference in what? Volume. So this is what happens in Boyle's law. We are saying that these gas molecules in this first container, when the piston is pushed down so that they have a smaller space to move about, okay, it means that the distance between the gas molecules is going to be reduced. And since they don't have so much distance about them, they begin to collide more with themselves and with the walls of their container. So that collision is what is bringing about an increase in pressure, because we have said that what? We have reduced volume by pushing down this piston. So pressure has what? Increased. So you see how they are indirectly proportional to themselves. Reduced volume is bringing about increased pressure. And if you are to further reduce volume, okay, like we see in this third container, we'll see that pressure will also further increase, because the lesser the volume, the higher the pressure, the higher the collision with themselves and with the walls of their container, so pressure will increase. That is what Boyle's law is telling us, that when we reduce volume, we are likely to what? Increase the pressure of the gas molecules. In other words, if this third container were to be made to come just the way this first one is, all right, we increase volume by pulling up the piston. What happens? Oh, the gas molecules will have more space to move about, so the pressure within the system will reduce. See that when we increase volume, pressure will reduce. So this experiment, okay, supports Boyle's law that at constant temperature, pressure is inversely proportional to the volume occupied by a given mass of gas. Now let us see a calculation based on this Boyle's law, okay? Now suppose you have 250 cm cube of a gas, okay, with a pressure of 550 millimeter mercury. Now find its volume, okay, if the pressure is increased to 570 millimeter mercury. So from what we have learned, you already know that because pressure has been increased, the answer you're going to get, the calculated volume you're going to get is going to be what? Reduced, because we say that they are inversely proportional. If one is increasing, the other one is reducing. So our answer at the end of the day, the volume we are going to get for this system is going to be reduced, less than what we had initially. Okay, so our pressure volume equation from Boyle's law, P1 V1 equal to P2 V2. Okay, now we are looking for V2. So if we should bring this equation at the right hand side of the equation to the left hand side, we would be having P2 V2 equal P1 V1. We are looking for what? Volume. V2, the volume at the end of the experiment. Okay, remember they gave us pressure at the beginning was 550 millimeter mercury. Volume was at 250 cm cube. Pressure at the end of the experiment was 570 millimeter mercury. So we are looking for what? Volume at the end of the experiment. So what we are looking for is V2. So we'll have this. When P2 crosses the equality sign, we'll be having P1 V1 over P2. So with this, we'll calculate our volume at the end of the experiment. All right? So Our P1 is what? 550, okay, 550 millimeter mercury, and the initial pressure, initial volume, our initial pressure was 550 and our initial volume was 250, okay, divided by what? The final pressure, which is 570. So the volume we are going to get, or our final volume, is going to be 241.23 cm3. So you see that this volume is what? Less than the volume we had at the start of the experiment. So this is a calculation based on Boyle's law. And remember, in the calculation you may be asked to find final pressure. The calculation may tell you to find the initial pressure, initial volume, as the case may be. Now, let us look at Charles' law. What does this law say? First of all, it is the temperature volume law. So this tells us that we are dealing with two variables, which are the temperature of the system and the volume of the system. So this Charles' law says that the volume of a given mass of gas is directly proportional to the Kelvin temperature at constant pressure. So for Charles' law, the variables that are constant here are pressure, okay, and of course the mass of gas. Okay, we are not adding any more gas molecules and we are not removing. So when we have fixed mass of gas and we have fixed pressure, this law is telling us that the given mass of gas, okay, is going to be directly proportional to the what? Kelvin temperature. So this tells us that it is directly proportional, okay? So it means that as one variable increases, the other also increases. When it is indirectly proportional, as we saw in Boyle's law, it is when they are in what? Opposites. One variable going up and the other one coming down. But here in Charles' law, we are being told that the volume to temperature relationship is what? Directly proportional. So as one is increasing, the other is also increasing. And as one is decreasing, the other is decreasing. So we have a mathematical representation of Charles' law where we have V is directly proportional to T. Therefore, V is equal to KT, where K is what? A constant. So with the graph, we can represent Charles' law as what? Volume temperature, where volume increases as much as what? Temperature is increasing. So Charles' law can be expressed in another form, which is what? V1 over T1 equal V2 over T2. So when we want to do any calculation on Charles' law, this is the formula we are going to be using. So Charles' law checks the effect of change in temperature on the volume of a given mass of gas. So if you have this given mass of gas and you apply heat, okay, you increase temperature by applying heat, what happens to the volume of the gas molecules? If you reduce the temperature, what happens to the volume as well? This is what Charles' law tries to tell us. So the volume of a gas increases as temperature increases, and it also decreases as temperature decreases. Now let us look at how kinetic theory explains this Charles' law. So considering a fixed mass of gas, okay, fixed mass of gas, remember the key word is fixed, okay, fixed mass of gas in a container with a movable piston. The piston should be such that it can move without any form of resistance, okay. Now at a given temperature, okay, we have a particular temperature at the start of the experiment, all right. Let's look at this image where we have this container, of course, with a movable piston given here, and we have a certain number of gas molecules in this container, and heat is applied. All right? When heat is applied, it means that temperature has what? Increased. The temperature of the system has increased. Because when we put heat into this system, what happens is what? The gas molecules gain more kinetic energy because of the input of that heat into the system. And now, because they have more energy, they are more energized to move about, collide with themselves and with the walls of their container. So when heat is applied, all right, the gas molecules will acquire more kinetic energy, move faster, and collide more with themselves and with the walls of their container. Now, this would lead to what? An increase in pressure. Definitely, when gas molecules are colliding and moving fast, that is what brings about what? Increase in pressure when they are colliding with the walls of their container. All right? Pressure is definitely going to increase. It's just like, let's use another analogy where you have maybe people in a particular space. All right? Imagine that activity increases, they get more worked up, the activity increases maybe in that place. You will see that that activity increasing is going to cause more pressure in that particular room. But say these people were removed from this small room and they were now put maybe in a larger room. Okay, that pressure that they exerted in a small room is going to what? Reduce, because the volume or the size of their room has been increased. That is what happens in Charles' law. Now, when this temperature is increased, okay, these gas molecules gain more kinetic energy. Pressure increases because they are moving faster, they are colliding with themselves and with the walls of their container. Pressure has what? Increased. Now that increase in pressure is going to what? Affect the volume of the system, so that what? The piston will move upward. Okay, remember we said that this piston is movable. All right, so this piston is going to move up because of this pressure that these gas molecules are what? Giving it. It's going to move up. And when it moves up, it means that what? The volume of the container has been what? Increased. So this piston moves up to this point. Now what happens when the piston moves up? It means that volume has increased. This increase in volume tends to what? Maintain and stabilize the initial pressure of the system. So when that excess pressure came as a result of increase in heat on this system, okay, that pressure is going to cause the volume of the container to what? Increase, all right, to cause that movable piston to go higher. And when it does, it means that these gas molecules now have more space to move about. And when they now have more space to move about, it means that their pressure will definitely increase. So the rate of collision with themselves and the walls of their container will reduce. So it's a way of what? Checking the pressure of the system. Charles' law says that fixed mass of gas molecules at constant pressure, all right, that what? The volume of the system is going to be what? Directly proportional to the temperature of the system. So, as even if the pressure increased due to the increase in temperature, the increase, okay, brought about when the piston moved up helped to what? Bring back that pressure to the initial pressure, so that pressure remained constant. So that is why we say that pressure is what? Still constant. Okay, so in that same vein, if temperature is reduced, okay, the molecules will move what? With a reduced what? Kinetic energy. So when you reduce temperature, of course, you're reducing the kinetic energy. The gas molecules will not be so energized anymore to move about like that. So when you remove temperature, the gas molecules will move at a reduced kinetic energy, okay? And this also means that pressure will drop and the piston will move downwards, reducing the volume of the gas. So this experiment simply supports Charles' law that says that at constant pressure, okay, the volume of a given mass of gas is directly proportional to the what? Temperature. So we saw from this experiment that when we increase temperature, volume also increased, all right? And when we reduce temperature of the system, the volume will decrease. So therefore, for n molecule of a gas, n could be any number. It could be 5 moles of a gas, it could be 10 moles of a gas, okay? Any particular number of gas molecules, when temperature increases from T to T1, volume also increases with the same proportion from V to V1 in order to keep the number of collisions per unit area of the walls of the container constant. And this long grammar, we are seeing here, number of collisions per unit area of the walls of the container simply refers to what? The pressure of the system. So volume increases so as to what? Keep the pressure of the system constant. Now let us see a calculation based on this law, Charles' law. At 42 degrees Celsius, okay, a sample of chlorine gas occupies 200 cm cube. What would be the volume, okay, at 150 degrees Celsius if the pressure remained constant? All right, so with our formula, V1 over T1 equal V2 over T2. So we are looking for what? The final volume. We say what would be the volume at this temperature, 150 degrees Celsius. Remember here, temperature has been increased, all right, from 42 to 150. It means that the final volume we are going to get when we are done with this calculation is also going to be what? Increased from 200 to whatever we are going to derive. So with this formula, our V1 was given at 200 cm cube. Our T1 was given at 42 degrees Celsius. But remember that we're supposed to be working with what? Temperature in Kelvin. Converting this 42 degrees Celsius to Kelvin scale, all we need to do is to say 42 plus 273.15, right? Remember when we talked about how to convert Celsius scale to Kelvin scale. So doing that, we are going to have approximately 315 Kelvin, all right? That's our initial temperature. And our final temperature was given at 150 degrees Celsius. Again, we'll convert it to Kelvin, and that will give us 423 Kelvin. So what we'll be looking at is what? Is our final volume that was not given. So with this formula, when we make V2 what we are looking for, it means that we'll be working with T2 V1 over T1. Okay, so when we put in these variables, our T2 was given to us at 423 multiplied by V1, which is 200. All right, divide T1, which is 315. 315. So when we do that calculation, we are going to be having 268.57 cm cube as our final volume. And as you can see, we went from V1 200 to V2 268.57. So we see that when we increase temperature, the volume also increased. So with this calculation, we have come to the end of this lesson. In our next lesson, we'll be looking at the other laws by Graham and Gay-Lussac and Avogadro. Okay, we'll be looking at those laws, and we also see some calculations based on those laws. So a quick summary of what we have learned in this lesson. We say that gas laws deal with how gases behave with respect to pressure, volume, temperature, and number of moles. All right, and some important gas laws are Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law, and Graham's law. We also say that Boyle's law states that the volume of a fixed mass of gas at constant temperature is inversely proportional to its pressure. Now we looked at Charles' law. Charles' law states that the volume of a given mass of gas is directly proportional to the Kelvin temperature at constant pressure. So now I'll be looking at some questions, all right, to help us with what you have learned today. The question is, the force exerted by gaseous particles per unit area of the wall of their container is dash. A, kinetic energy. B, gas pressure. C, constant pressure. The answer to this question is B, gas pressure. In the course of our class, we say that the force exerted by gaseous particles per unit area of the walls of their container is known as what? Gas pressure. Another question. The law that gives the relationship between volume and temperature at constant pressure is dash. A, Charles' law. B, Boyle's law. C, Graham's law. Well, if your answer was B or C, you're wrong. Our answer is Charles' law. Remember, Charles' law is the law that shows the relationship between volume and temperature of a gas system. So with this, we have come to the end of this lesson. See you in the next lesson. Thank you.